Water treatment and desalination. Our project is located in Bali, Indonesia, where 500,000 people suffered from the water scarcity. Bali's water resources are not evenly distributed across different geographical areas in different seasons. Moreover, the distribution of water resources used by different industries is not the same. Meanwhile, the amount of water used varies greatly from industries to industries from season to season. Bali's total population is large, dense, and unevenly distributed. All this exacerbates the problem of water scarcity in this region. The areas of the island that face water pollution are shown on the map. The coastal areas also face the problem of backed-up seawater. We designed a water cycle system in Bali using the total water cycle management in Brisbane as a reference. I was responsible for designing the water purification system and the desalination system. The distribution of the completed sewage treatment plants on this island is shown on the map. We will build 8 new sewage treatment plants to meet the water shortfall. A new solar desalination plant will be built. The desalination plant uses solar energy as its energy source. It also used surplus magnesium in the local rocks to produce magnesium oxide, which absorbs its emissions and the carbon dioxide already present in the atmosphere. This is the entire process of desalination in the desalination plant, and shows the amount of CO2 emitted at each step. We have chosen Denpasar, the capital of Bali province, as the showcase for our project. Yellow for desalination plants and red for sewage treatment plants. Meanwhile, we have planned a water supply system for the area according to the distribution of the population. Next, we show you the water treatment system concentrated in the southeast of Denpasar. This is a cross-sectional view of the water treatment system. We have planned it according to the topography, with the seawater treatment plant to be built on the shore and the sewage treatment plant to be built in a more inland area. In addition, we have designed the desalination plant for home use. We are able to use it to desalinate seawater in our own houses. It is powered by solar energy and has a portable design. It is very easy to handle. In a home, we can use it not only to provide us with drinking water, but also to provide water for domestic use. According to our calculation, 8 sewage treatment plants produce 10,785 tons of CO2 per year, while one desalination plant is capable of treating 18,200 tons of CO2 per year. Each year, we are able to reduce 7,414 tons of CO2.
Our study area is located in Bali, Indonesia. Urban floods and waterlogging is a serious problem. Most urban areas are affected by floods and rainfall. The main strategy is GI, LID, and water plaza, which from the large scale to small scale. The objective is to achieve a sustainable stormwater management circle by 2045. Strategy 1 is GI, green infrastructure. Existing GI in Bali is forest land, grassland, wetland, shrubland, mangrove, and some parks. Some farmland also can be used as green infrastructure, like some paddy fields. Then increase and build some parks, like forest parks, wetland parks, small parks. In urban area, also need to increase green infrastructure. Then, the main riparian areas will then be rehabilitated with GI. At the same time, increase many wetlands. After that, zoom in to Denpasar. There are different kinds of wetland. Functional wetland, urban landscape wetland, farmland wetland, coastal wetland, river wetland. Then 8 more small wetlands to form a network. Throughout Bali, we need to establish protected areas, key recovery areas, special areas of conservation, special protection areas. Finally, in 2045, create a network of green infrastructure. GI is accessible and connection. Strategy 2 is LID, low impact development. In Bali Island, most urban areas are affected by floods. Urban waterlogging is a very serious problem. LID facility can make a big difference. The main project focused on Denpasar. Concept of LID is protective design and low-impact landscape to achieve penetration, runoff storage, filtration, and biological retention. LID have many facilities, which from physical process to biological process. The large label number will reduce more runoff. Then, with selection of facilities in urban road, green space and square, building and community. After that, choose a specific study area in Denpasar to use LID facilities. Master plan shows green roof, green garden, constructed wetland, permeable pavement, water collection tank, water plaza, and main road. Then create a community rainwater system. I will show some details of LID facilities. Constructed wetland can filter and permeate rainwater. It also has landscape function. The filter tree ponds can filter and permeate rainwater beside the main road. Permeable pavement is suitable for parking lots and sidewalks. Green wall can control water flow and filter sewage. Rain garden can collect rainwater and control stormwater, also retention and filtration of rainwater. It should choose native plants in the tropical region of Bali and be resistant to waterlogging and dry out. Green roof deal with the source of rainwater runoff. Plants' strong adaptability to climate conditions and functions should to be selected. Finally, rainwater collection is also important. Storage tank can usually used to store roof rainwater. Strategy 3 is water plaza. It has different types of reservoirs to collect rainwater. The dry seasons and rainy seasons have different situations. The water plaza can store water and also can be activity space. So the water plaza should be mainly built in high-density urban areas, mainly in Denpasar. In short, the overall strategy can solve the problem of urban floods and waterlogging in Bali, achieve the sustainable circle of stormwater management in 2045. At the same time, it can effectively reduce greenhouse emissions. Although the construction of GI produces many carbon emissions, but it is enough to achieve the goal of reduced carbon emissions in 2045.
Bali is an island with a tropical rainforest climate and abundant rainfall, where many areas are influenced by flooding. Rainfall, ground type, and garbage accumulation are the main reasons affecting flooding in Bali. This map shows the severity of the impact of flooding throughout Bali decreases gradually from the coastal areas to the inland areas. This is the precipitation in Bali from January to April. The southern coast has high precipitation all year round. This is a population distribution map. The large amount of human activities will bring more garbage accumulation. This is a map of the land use types. The southern area where there is a lot of population activities is basically artificial surface and farmland with poor infiltration capacity. There are two general ways to deal with flooding. The first is to build dams and reservoirs, and the second is ecological flood control. This is the distribution of reservoirs in Bali. There are significantly more reservoirs in the flood-affected southern region, and are generally located near artificial surfaces and farmland. Vegetation for ecological flood control absorb carbon dioxide and reduce carbon emissions, which in turn reduce evaporation. This will further lead to a reduction in rainfall, resulting in a lowering of the water level and reduce the threat of flooding. Bali's mangroves are a great model for ecological flood control. The well-developed root systems of mangroves help to slowing down the water flow and eliminating waves. However, the area of mangroves has been reduced due to urban development in recent years. To better resist flooding and restore the ecology, We plan to cultivate mangroves and other tree species along the shore for ecological flood control. We plan to design a shore embankment in terraced form and plant vegetation to resist flooding and increase infiltration capacity in an ecological way. This is the infiltration capacity of different land. We want to change some parts of the ground types and plant trees in the area most affected by the floods, the coast of Denpasar. This is the flood-affected maps of Denpasar. Some urban ground infiltration and water storage design have helped mitigate flooding impacts. We plan to design some infiltration pavement in urban areas in 2045 to reduce pressures in the area most affected by flooding. In general, the excess water is treated by means of water storage devices installed under the urban road surface and vegetation on the road surface, and the water is recycled through pipelines. In 2045, we expected an increase in vegetation of about 1,500 hectares. These plants can help Bali absorb 39,715 tons of carbon dioxide and increase 1,050 tons of carbon fixation per year.
In the first part, I introduce Ubud water pollution treatment program, which uses case of Subak in Ubud. The whole structure is divided into 3 parts. In the first part, the background of water problem will be shown. Ubud is located in a coastal area which requires a lot of water. Meanwhile, water resources is relatively unproductive. Water flowing downstream through Ubud causes plastic pollution. Ubud is located in an area where the river is polluted. Ubud has a high average daily plastic waste generation and a low waste recycling rate. The soils of the farmland in the Ubud area are difficult to infiltrate, resulting in poor soil absorption and the retention of pollutants in the river. Farmland in the Ubud region is relatively sensitive. Ubud is located in a farming area and is one of the more concentrated areas of Subak. The overall carbon emission in Bali maintains in a stable situation. However, the increasing number of visitors also brings rubbish that causes water problems such as contaminated underground, etc. In the second part, I will introduce detailed studies in a specific area. The overall problem of water is scarcity and pollution. Subaks in the Ubud are close to the city. They have easy access to water for residents in the city and a good location for a sewage treatment station. The high number and density of Subak facilities, the unfilled collection of and treatment of water resources. Here I will introduce the whole procedure of water treatment. 6 different scenes are demonstrated to showcasing different scenarios of water management. Water flows uses gravitational potential energy from the arable land at a high level to the treatment plant at a low level. Overall, the wastewater in Subak will be treated in different ways. Water from agriculture fields is simply filtered into sitters and then transported to residential areas. The plastic contaminated river water in Subak is initially screened upstream by means of a barrier nets to remove the plastic waste visible to naked eye. The remaining water is then transported to the sewage treatment plant, while the plastic waste is efficiently disposed of. The third part are 3 conceptualization of comparison of before, during, and after the treatment process.